Oh, welcome back to what has become a video 1B of my transition metal videos. Where in the first video we talked a bit about coming up with three-dimensional structures for our first transitional complex, and we came to this idea that there are two isomers, two different octahedral geometries that are possible. And in the second video, we'll talk through coming up with three-dimensional structures for these other two transition metal complexes. And so I'm going to dive into that. And so actually I like red for annotating these things. So as we said last time, we want to focus on what's going on within the square bracket. So what's going on here is that we have a metal, a transition metal, iron, and if you're unsure which one the metal is, you can always go kind of scrolling through your periodic table and be like, oh, look, like there's iron. And in case you were worried, like there's cobalt. I wasn't lying. It is a transition metal. Right, so iron is in this D block. It is a transition metal. It makes transition metal complexes. So we have iron as a central atom. And then attached we have six Fs. F being fluoride. So in analogy to the Cl meaning chloride, the F means fluoride. That is what's going to be attached to our metal. We'll talk a bit more about those Ks on the outside of the brackets in a moment, but we want to focus on what's inside the brackets, find our metal, figure out what's attached, how many things. Once again, we have 6 things attached to our metal. Steric number equals 6. We should have an octahedral complex. And so I'm going to throw an iron in the middle, and I'm going to write out a skeleton for an octahedral complex. And then I'm going to start attaching things to it. In this case, I've only got fluorine, right? I've only got fluoride. And so in analogy to before, we're going to say, all right, we're going to take one of those lone pairs and we're going to use it to make a bond to the metal. And so what that leaves us with is fluoride, where we had 4 lone pairs up here, but now there's only 3 left, because that 4th lone pair is being used to make that bond. Right? Like that's kind of where that lone pair ended up. Those 2 electrons are now making that dative bond, or that coordination bond between Fl. Oops, it doesn't have an Fl. It's just F. That's silly. You'd think I would know that. It's because I have chloride on my mind. Between F, fluoride, and the iron, Fe. Cool. I then do this 5 more times. There's an F here, there's an F here, there's an F here, there's an F here, there's an F here. Very often with these structures, people will omit drawing in all of the F lone pairs because they don't serve like that much purpose in the drawing. But since this is an introductory video, I'm going to draw them all in so that we're clear that in all cases we have an F with 3 lone pairs, and what used to be the 4th lone pair is now making a bond to the iron. Oh, and I realize I forgot to put the positive charge in that other structure down here earlier. But anyway, and so the last piece of this is to just think about what is the charge on this compound, and that's where the K's come in. So when we have things that are outside the brackets, when we have things like K outside the bracket, what that's saying is that there are 3 associated with the complex. Like that's kind of what it means to have those 3 Ks outside the brackets. And so the thing to keep in mind is the stuff outside the brackets pretty much always exists to balance charge. Right, like when we're looking outside the brackets, we're pretty much always looking at ions that are going to balance the charge of whatever is inside the bracket. And so if we have 3K pluses outside, that means that the outside charge is 3 plus. And so the inside, the bracket, has to balance. Right? Because overall, there is no net charge in K3 Fe F6. So if there's plus 3 outside the bracket, then the stuff inside the brackets must be -3. Because if I have -3 and +3, that balances and gives me a net charge of 0. And so all this was a long-winded way of saying when we actually think about how to draw this complex, this is an iron complex with 6 fluorines on it that has a -3 charge, and then there are 3 K pluses floating around. I don't know why I just did that funky thing. And the way you denote those K pluses floating around is you just kind of write there's some K pluses floating around. They are not attached to the iron. They are not attached to the ligands. They are just in the vicinity to balance the charge. And that's the ball game. All right. So that's compound number 2. I'd like to move on to compound number 3. And this compound, I really chose to kind of make us go to the ligand table because they're going to kind of use some common abbreviations of ligands that show up in your table. And so in this case, there are no brackets. If you have compounds that are uncharged, where there's no net charge, and there's no balancing ions around, oftentimes brackets will be omitted. We can still look for our metal, and our metal is platinum. And what's attached? And the things that are attached now might be a little funky. We have an NEN and then 2 CNs. So the question is, what the heck are those things? If you encounter a problem where you're like, what the heck is that abbreviation? What's going on? The place to go is, your class notes are a great place to go, but this table in Chang is often going to be very, very helpful. So what we're looking for is the N. I think probably you'll need to find for you in class, but this is a very common abbreviation. N means ethylene diamine. This is N. And it's this structure here attached to the metal. Let's go up and say, all right, so N is this thing. One, two. And if we're wondering to ourselves, like, where is this attached to the metal? Remember that to make a bond to the metal, we need lone pairs from the ligand to donate to the metal. And the really key thing to recognize here is that there's like 2 different positions on this ligand that can donate to the metal, and both do. This is called a bidentate ligand. because there are two positions on the ligand that bind to the metal. When we go to put this ligand on the metal, basically the nitrogens have to be able to reach. They need to be, and so, yes, I'll talk more about this in a few minutes. Okay, so this is just like an example of how this thing binds to platinum. It's not a full version of the geometry. We then also have two CNs attached to our metal complex. What is a CN? And so kind of scrolling down here, what we have to find is, right there, that is a CN, right? Like that's the kind of formula for that Lewis structure. It's cyanide. You will very often see this cyanide abbreviated as CN. These things are cool. They have it's a triple bond between C and N with a lone pair on each side. In the table, it doesn't actually show you which atom the formal charge is on, but it is on the carbon. And when you go to bind this thing to a metal, you bind through that carbon. Like generally speaking, like that lone pair is more reactive. That lone pair is the one that goes and attaches to the metal. It's also why it's written as CN, where like the C is kind of closer to the metal. Oops, I didn't mean to delete that bracket. I was just meaning to highlight that the C kind of suggests that that's what's attached to the metal. All right, so we're going to put two of these CNs on platinum. And before we do that, we need to figure out what the geometry is. So far, all I've really shown is that, like a bidentate ligand bites twice. It goes on the metal twice. What is the geometry here? So what we have is, because the bidentate ligand attaches in two positions, right? En really accounts for 2 in our steric number, right? Because there's actually one nitrogen attached to, right, one atom bonded to the platinum, and a second nitrogen attached to the platinum. And so that's, I don't know, that's tricky, right? It's one ligand, but it adds 2 to the steric number. The CN is a monodentate ligand. It binds only once. And so the total number of things bound is 4. The steric number is 4. And that raises the question of, is this a tetrahedral complex or a square planar complex? You are not in a position to predict which one of these is going to form. Or to the best of my knowledge, you are not in a position. It could be that one of the professors is, teaching above and beyond, and that's wonderful. And so generally speaking, in these circumstances, you will be given which one of these is it. In this case, this is a square planar complex. It's a steric number equals 4 complex. You are not in a position to predict whether it's tetrahedral or square planar, but I went and looked up what these complexes look like, and they are square planar. So that's how we're going to draw it. How many different ways can we draw that square planar complex? That's the very last part of that kind of problem I want to walk you through. And so I'm going to move down here where I have more space. I said, all right, I've got a platinum complex. I need my bidentate ligand to go on, and first I'm going to redraw it the same way that I drew it before, right? And I'm just going to put in those 4. I want to highlight that, like, another, at least what seems like a possibility, is, maybe here's my square planar complex. Maybe there's an N here and another N here. It can at least occur to us that this is a possibility. But if we do this, right, like those two N's are 180 degrees apart, that cannot happen. Like, it should look really funky when I draw it. It is too far from this end to this end right now. It's not, there's a 180-degree relationship. That 2-carbon bridge in the backbone, this bridge of like 1 carbon and 2 carbons that are attaching those ends, it can't reach all the way over the top of the platinum and around to the other side, 180 degrees away. This is not possible with a bidentate ligand. I have to have the 2 ends on the same side. The 2 ends have to be next to each other. They have to have this smaller angle relationship. So here, this is a 90-degree relationship. Here, this is a 180-degree relationship. And it's just not possible. This is all a long-winded way of saying no. Hopefully that's enough X's to make it clear that that can't happen. You could also try making a model of this. You could take one of your metal atoms in your model kit, put it in the middle, make your N the way I did it up here. Like, you can make a model of that and then try to stick it onto the metal, and you will see that only this one is possible and that other one is not. Okay, that's my last X, I promise. So then all that's left to do is to put the cyanides on here. And so what we said is that this lone pair on the C is the one that makes the bond to the metal. And so we go like this, and we go like this. And this is the only possible square planar geometry that I can draw for this platinum ethylene diamine dicyanide complex. And that will conclude videos 1A and 1B. And in the next video, I'll talk about assigning oxidation state to the metal atom in the center of all 3 of these complexes.